All right, let's go ahead and talk about how we can use the right-hand rule to figure out the direction of the missing parts in magnetism problems. Let's say, or let's actually come down to a very important conclusion. If you can imagine your right hand, let's call the thumb right here the velocity. Let's imagine that the thumb shows the velocity. Let's imagine the palm of the hand shows force, and the other four fingers just indicate the magnetic field. So the direction in which your other four fingers move, or just the way they are, indicates the magnetic field itself. So thumb shows the velocity vector. The palm of your hand shows the force vector, and the four fingers, or the other four fingers, essentially show the magnetic field intensity, or the magnetic field itself. Now, why do we have such a problem when we want to discuss the vectors of a moving charge in the magnetic field? Well, the reason is pretty clear. It turns out that this is a three-dimensional vector, and in order to show it on paper, we have to use special cases or special symbols, where we know that if we use a cross symbol, that means the magnetic field, or whatever the thing is, maybe it's even a charge, it's moving into a page, and a dot indicates the fact that that vector is coming out of the page. So if a line was coming right out of your screen right now, we could say that it's coming out of the page. And if it's going right into the screen, we could say that it's going into the page. And if something is basically moving above it, like going upwards, then that something would be at 90 degrees with the out of the page or into the page thing. For example, it could be the velocity vector, and the vector that's going into the screen could be the force. So you can kind of imagine the vector looking something like this. So if you have a normal plane, the force vector would be like this, and whereas the magnetic field vector is in this direction, and the velocity vector could be in the other direction. And the angle between the force and magnetic field vector is the theta that we use in the formula F equals to QVB sinus of theta. Now, let's go ahead and solve a couple of problems. The thing is, let's say, for example, we have an example in which the force is going into the page. So the palm of your hand should be going into the screen. If the palm of your hand is going into the screen, make sure that the thumb, right? So let's say the force is going into the screen, and then the velocity vector is actually to the right. So in such a scenario, your thumb should be facing the right side. The force vector is coming out. And if you were to place your hand right on the going into the page part, basically what would happen is the palm of your hand would be facing your own face, and your thumb would be facing the right side, which indicates the fact that the four fingers are indeed upwards. And that would be the direction of the magnetic field. Let's do another example. Let's say we have a magnetic field that's going into the page, whereas the particle, let's say it's a proton, and it's moving upwards. So how can we find out the direction of force? Well, the four fingers should be going into the page, and if you do that, your four fingers are essentially going into that cross symbol. Your thumb should be facing upwards now, which indicates the fact that the palm of your hand is actually going to the left, and that would be the direction of the force vector. Now, let's imagine we have such a scenario in which we have a piece of wire that is carrying current. We know that there's always going to be a magnetic field created around straight wires that are carrying current. Now, let's imagine the direction of force, or let's say the direction of, for example, an electron is going into the page, right? So we have an electron that's essentially going into a page with a certain velocity. Or we could say this, we could say an electron is going to the right, and we have a magnetic field that is directed into the page from the right side, because we know that if you were to grab this piece of straight carrying wire, then if you were to kind of swing your four fingers on the right side, the magnetic field would be in the directed inwards, whereas it would come out of the left side. But since the electron is moving to the right, let's imagine the direction of the force. So your four fingers would essentially have to be facing into the page, and the velocity vector should be going to the right. So your thumb should be facing the right. If you do that, the force would be upwards. However, this is a negative particle. For negative charged particles, you have to reverse the direction of force, and that's a very important thing that you gotta remember. So the force would actually be downwards. So keep in mind that for negative charges or for negatively charged particles like electrons, the direction of the force should be reversed. Reverse the direction of force. Let's do one final example. Let's imagine we have a magnetic field that is directed inwards. So we have a bunch of inwards magnetic field like this, and we have a piece of electron that is going to the left with a specific velocity. So the velocity vector is to the left, and the magnetic field is into the page. Out of the page. Now, if you do that, your thumb should be facing left, and your forefinger should be going up. The back of your hand should be facing your face. Now, if your thumb is going to the left, then you're doing this correctly. However, since this is an electron, the direction of force, which is actually going above or upwards, should then be reversed to downwards. So the force is actually downwards in this scenario. That's it. Thank you for watching.